Hi there, my name is Christopher Worst and welcome to the first video of the fifth and final homework for Transport 1. This video is going over part 1, which which poses the situation of water flowing along an aqueduct with a width of W, inclined at an angle relative to horizontal, at a volumetric flow rate of Q. Assuming the shear stress of the wetted wall to be equal to that of an equivalent circular pipe with the same average velocity, derive an expression for the height h of the water flowing along the aqueduct. Write Python code using SciPy optimize.root to solve for h when the width is 0.5 meters, q, the volumetric flow rate is 1 meter cubed per second, and the aqueduct is inclined 15 degrees relative to horizontal. So I have my whiteboard behind me, and we're going to start by drawing a picture, and then we're going to start derivating out the equation that we're going to need for the coding. Alright, so first and foremost, we're going to start with the picture as usual. So we have, drop and get out of the way. A rectangular channel of some width here, W, water flowing out the end. We have our height of the water here. This is what we want to find, this h. This is angled at some angle relative to horizontal theta, and then the length of this channel is delta x. So we have that. So, as with most cases when we're doing fluid dynamics, we're going to start with the Bernoulli's equation. We've already fully derivated out the version that we're going to be using in this one in another video. So we have pressure at state 2 minus pressure at state 1 over the density minus the velocity at state 2 minus velocity at state 1 over 2 plus gravitational constant times the change of the height state 2, or y position is state 2, y position is state 1, equals, we're going to be using the, we've got 4 times the fanning friction factor times the length delta x over the diameter of the pipe. This will come into play later, times the velocity squared over 2. By the way, these two velocities are squared. Not that it matters, because the velocity is average or the same in both states, but we also know that because this is open to air, pressure at both states are equivalent. So first we're going to multiply this across, but then these will cancel out. So this is going to go to yes, here. So rho, the density times gravitational constant times z2 minus z1 equals 2 times the fanning friction factor times delta x times the length times the velocity squared divided by the diameter. Now this z2 minus z1, the difference in y positions in state 2 and state 1, is actually hidden here. The fact that we have a triangle here, and we can just use sine theta is equal to height over the hypotenuse. So hypotenuse times sine theta, the length delta x times sine theta is equal to this here. So we've got rho, density times gravitational constant, times the length times sine theta equals 2 times the Fenton friction factor, length over, times velocity squared over diameter. These two lengths cancel, which means we have density times gravitational constant times sine theta is equal to 2 times Fenton friction factor times velocity squared over diameter. Now we're just going to get gravitational constant alone because we want to do a circular approximation, which is going to involve g specifically, the gravitational constant specifically. So we have gravitational constant is equal to, in the Bernoulli's equation, or this scenario, 2 times the Fenton friction factor times velocity squared divided by diameter times the density times sine theta. Now from here, again, we're going to want to do a circular approximation, so I'll draw another picture here. Circular pipe with length of delta x. Water is flowing through. So, brush should be here. No. Here, multiply. Yes, okay. So, there should be a row in this. So this will cancel. So, this density is here, here, and here. It's not there. So, there. Anyways, so in this case, in a completely separate scenario, the volumetric flow rate is equal to the density times the gravitational constant times the volume, which is just the area times the length. So area times the length of delta x is equal to the shear stress times WP, which is this wetted perimeter, i.e. how much of the wall is wet, is in contact with the liquid, multiplied by delta x. So these delta x's cancel, and it goes to density times gravitational constant times area is equal to the shear stress times the wetted perimeter. You can also get G alone again to say that gravitational constant is equal to shear stress over density multiplied by wetted perimeter over area. We're setting this value alone because we actually know the values for this. The wetted perimeter here is just a slice, so it's a ram. It is the circumference of the circle, so that's pi d or 2 pi r. We have diameter over here, so we use pi d. So that goes to gravitational constant is equal to shear stress over density multiplied by pi times diameter divided by area, which is just the area of a circle, pi times diameter over 4, pi times diameter squared over 4. These pi diameters cancel, goes to gravitational constant equals, at least in the circular approximation, equals the shear stress divided by the density multiplied by 4 over the diameter. And we can only do this because in the question it made sure to say that the wetted perimeter and the shear stress is the same in this in the rectangular channel as a circular channel or circular pipe. So we have this gravitational constant here, we have this gravitational constant here. We can now move along to tau, the shear stress. So that goes to tau, or 4 times the shear stress divided by density times diameter equals 2 times the Fenton friction factor times velocity squared over diameter sine theta. these diameters square, cancel, goes to, and if we want to get this alone, we multiply cross, goes to tau, the shear stress is equal to the fanning friction factor times the velocity squared times the density of the fluid, divided by 4 sine theta. This 4 cancels with this 2, so it's just 2 sine theta. So now, from here, we know from earlier that if we were to take this, or this specifically, tau is equal to density times gravitational constant divided by the wetted perimeter divided by the area. Now the wetted perimeter over area in this case is going to be specifically for this rectangular channel, which is different from what we used earlier, so it's actually going to be, and I'll put it in as well, it will be density times gravitational constant is equal to fanning friction factor times velocity squared times the density divided by 2 times sine theta multiplied by 2h, 2 times the height of the liquid, 2h plus the width of the channel, the width of the liquid, divided by wh. Width times height of the area, therefore the area of a rectangle. So, from here, these two cancel, and we get back to g is equal to the fanning friction factor times v squared times the velocity squared divided by 2 sine theta multiplied by 2 times the height plus the width divided by the width times the height, which is the area. So we have this here. Now, to get this fanning friction factor, we have our Churchill equation, so we'll just call it F. This is dependent on the Reynolds number and the that ED constant we calculated earlier. The Reynolds number is rho VD over mu, density Reynolds number equals density times velocity times diameter over viscosity, and we need this d again. We don't have a value for it. So we have this wetted perimeter divided by area, per area, which we know is the same in both the circular approximation and our actual real situation. So wetted perimeter divided by area is equal to, we found this earlier, 4 divided by the diameter. It's also equal to, as we found earlier, 2 times the height plus the width divided by the width times the height. That means that these two cancel. That means diameter, if we flip this, that diameter equals 2 times the area divided by, oops, no, that is 4 times the width, times the area, the width, the height, divided by 2 times the height plus the width. So we have this diameter equation here, the diameter of a rectangle, which we, kind of weird if you think about it, but the last thing that the question asked is for us to find Q in here. So as we know, the volumetric flow rate, Q equals velocity times the area. That means that velocity is the volumetric flow rate divided by the area, which if we plug into here, means that gravitational constant is equal to the fanning friction factor times the volumetric flow rate squared divided by the 2 times sine theta multiplied by 2 times the height plus the width divided by width times height cubed. because the area is just width times height that is squared, and that plugs in here. So now we have this gravitational constant, which contains height in it, so we can use that in our code. We have a diameter equation, which also has height in it, and we have a Reynolds number that can be used to find the failing friction factor here in the Church's equation. So with all of that done, we're going to move over to the coding now. All right, so to begin our coding, I'm going to start with the usual import numpy as np. We're also going to import the root solver. So from scipy.optimize, import root. That should be all we need. Cool. So the Reynolds number, as usual. I also have notes over here of just the equations that we had earlier because I'll need to plug them all in. Reynolds number is rho v velocity diameter mu. And then we also need g, the gravitational constant. Okay, so we have rho here. So we have rho equals the density of water equals 1,000 kilograms per cubic meter. Mu equals 1e negative 3. And then g equals 9.81 meters per second squared. Okay? As I mentioned earlier, we are going to need the Churchill equation. I just copied this over from a previous section. This will input the Reynolds number and give the ED, and it will give us the value for the fitting friction factor. So, per the homework, we have a volumetric flow rate Q of 1 cubic meter per second. We have a width of 0.5 meters, and then theta equals 15 degrees. We're going to need to do sines, so we're going to also want to turn into radians. So numpy.pi divided by 180. That should be good. So all we need to do now is to define a function to put into our root solver. So define right-hand side, it takes the vector. We want h, we are looking for height, and we're going to need to give an initial guess. So height is equal to vector value is 0. From this, with all of this, we can find the diameter. Diameter, what did I put it? Yes. Diameter equals 4 times h times w divided by 2 times h plus w. And just split it up a bit. There. With the diameter, we can also find the velocity. We know that v is equal to q divided by a, or q divided by height times width. With that, we can find the Reynolds number. So Reynolds number is equal to rho vd over mu. So rho times velocity times density divided by mu. With the rho, we can find the Churchill equation. So F is equal to Churchill, if I could spell it right, the Reynolds number, a roughness factor of 1e negative 6. And with that, we have everything we need. Return, what was the final equation? We want g F times Q squared times 2 times H plus W divided by 2 times numpy dot sine theta times HW, H times W, height times width cubed. No, nothing there. Good. So we can root our, we want our vector and a variable of, call it 0.1. And shift enter. No, vec is, oh, right hand side, not vec. Right hand side. There. I'm not making good progress. I'm missing something here. Yes. Number one, this needs to be a vector. Number two, we need to actually give it something to root. There. Should good. It converges. The array will give it point x 0. That the height is 0.2443 meters in the channel. So, with that said, thank you very much for watching. I hope you have a wonderful day.